Okay, so we were at this stage, right? In the above problem, we have a 3000 students, population is 3000 and it is normally distributed. Okay, its mean is 68 and standard deviation is 3 is given. 80 samples are taken, each sample size is 25. Okay, and in this problem we computed mean and standard deviation of the sample and distribution of the means with replacement and without replacement. After that, see, okay, this one, right? So whether it is with replacement or without replacement, mean is going to be same 6. Okay, it is going to be 6 only, you see. Whereas standard deviation also we got. Okay, this is the problem or what? I think this one, no? Yeah, right, this one. Are you able to hear?
Yes.
Yes, yes. Okay, so now you see, whether it is with replacement or without replacement, mean is going to be same. This is 68 and see 0.6 standard deviation is 0.6 with replacement, and without replacement also it is 0.6 when you round to 2 decimals. So that's what I was telling. Okay, so as long as the population is coming from, as long as the population is normally distributed, we always by default take this formula sigma by root n. We don't need to take this formula. Okay, because almost these values are same. Okay, so after that, this is the formula for the standardized random variable for x bar. Okay, which is x bar minus mu x bar by sigma x bar. Mu x bar is mu, sigma x bar is sigma by root n. That is what I was telling. Okay, and mu is 68, sigma by root n. Okay, sigma by root n is 0.6. Is this 0.6 or any, did I do any mistake? What is sigma?
Point.
And I think we haven't divided with okay, here itself. Okay, sigma x bar 0.6. Okay, right, sigma is 3, root n, so here itself I computed 0.6. Fine.
Yes.
So these are the standard scores for 66.8 and 68.3. Okay, so when you substitute these values here, you will get these z values. Later I computed this normal probability with the standard normal probability using standard normal distribution table. Okay, and this is the second one. Okay, second one is about less than 66.4 inches. Less than 66.4 inches. What is the probability that sample mean is less than 66.4 inches? So for 66.4 inches, you compute the z score. Okay, so this is the z score you got. So x bar less than 66.4 is same as saying that probability z less than minus 2.67. I converted this into standard score, and using normal probability z less than minus 2.67 is same as saying that z greater than 2.67 using symmetry. And right tail is nothing but 0.5 minus the area between 0 to 2.67. Using distribution table, you will observe that the area between 0 to 2.67 is 0.4962. So when you subtract, this is the probability. And if you're asked to find out the expected number of samples whose mean is less than 66.4, means you have to multiply that total number of samples with the probability that a sample mean is less than 66.4. So when you multiply 80 with 0.0038, you are getting something around 0.3 something. So 0.3 is rounded to 0. Okay, so this is a second bit. Now remaining problems are also similar. See, what is the fifth one? Determine the probability that x bar will be in between 75 and 78 if a random sample of size 100 is taken from an infinite population having mean 76 and variance 256. Okay, so nothing is mentioned about the normality of the population, but if you observe that the sample size is 100. So because it is a large sample, okay, the distribution is going to be, if not normal, it will be almost normal. Okay, so we can approximate this with the normal probability as long as the sample size is large. Okay, sample size is large and standard deviation is given, you can always use the normal probability. That is what I did here. Given mean is 76, variance is 256. So under root of variance is standard deviation is 16. Sample size is 100 given. You're asked to find out that sample mean is in between 75 and 78. So I computed standard scores for 75 and 78 here. Okay. This 75. So I substituted 75 here. You get one Z score. You substitute 78 here. You'll get another Z score. Okay, this is a standardized variable. Okay, mu x bar is mu is nothing but 76, and sigma x bar is sigma by root n. What is sigma? Sigma is 16 and n is 100 under root of 100. So 16 by 10 is 1.6. Okay, so corresponding using this formula I computed these Z scores by substituting 75 and 78. And once you have the Z scores, rest is just routine normal probability calculation. Okay, so probability that sample mean is in between 75 and 78 is nothing but probability that the standard normal variable is in between minus 0.63 to 1.2. Because one is negative, other one is positive, you have to add the probabilities using normal distribution table. You will observe that the probability is 0.6301. Is this clear? Shall I proceed?
Yes, sir.
Okay. So next one is also similar. Find probability that x bar greater than 66.75 if a random sample of size 36. Again, you observe that whenever data is given, you first see the size of the sample. Two things you have to see: what kind of, whether it is small sample or large sample. Next one is whether sigma known or unknown. See, this problem is about sigma known or unknown. Okay, so sigma known means what? What is sigma? Sigma is population standard deviation. Okay, so sample size is large sample and mean is given, population mean is given, population standard deviation is also given. Therefore, it is a problem related to sample and distribution of means with a sigma known. Okay, so that's what here. Okay, sigma is 9, mean is 63, sample size is 36. Again, this is the standardized random variable x bar minus mu by sigma by root n. Mu is 63, sigma is 9, root n, root of 36 is 6. So 9 by 6 is 3 by 2 is 1.5. So x bar minus 63 by 1.5. So you're asked to find out this normal probability. Therefore, you find out the Z score for 66.75. Substitute here. You'll get 2.5. So sample mean greater than 66.75 is same as saying that Z greater than 2.5 corresponding to standard normal probability. And right tail greater than means right tail. Right tail is nothing but 0.5 minus area from 0 to 2.5. Again, look at the standard normal distribution table, and you'll get this probability. Okay. Again, see the last one. Calculate the probability that a random sample of 16 computers. Again, is it a small sample or a large sample?
Small.
Small sample. Because a small sample means n must be less than 30. It is a small sample. Make a note. And we'll have an average life of, he is asking about less than 775 hours, assuming that the length of the computers is approximately normally distributed. Okay, he is asking us to assume that it is almost normally distributed, asymptotically normal, with a mean and standard deviation. Standard deviation is given. So whenever the standard deviation is given, and so we can okay, because it is given approximately normally distributed, we can use again normal probability. Whenever sigma is known, we always compute the probability with normal probability only. Okay, irrespective of the sample is small sample or large sample. So mean is 800, sigma is 40. Number of computers are 16. You're asked to find out the mean lifetime of computers average life of computers is less than 775 hours. So this is a standardized variable. X bar minus mu by sigma by root n. Mu is 800, sigma is 40, root 16. N is 16, root 16 is 4. So 40 by 4 is 10. So corresponding to 775, you compute the standard score, again minus 2.5. So z less than minus 2.5 is same as saying that z greater than 2.5. Right tail again 0.5 minus probability from 0 to 2.5, again you got a 0.0062. Okay, so almost all problems are similar, right? So you just have to take the data, okay, write the standardized random variable for the sample mean and compute the z scores, and use your normal distribution table to compute the probability. Is that okay?
Yes,
Shall I
sir.
proceed?
Yes, sir.
So how do we understand this? How do we proceed when some problem is given? So the whole topic is about sampling distribution of mean, single mean, okay? Because you are going to see difference of means and so on. So sampling distribution of single mean, okay? Single mean. So when it is given like this, so ask yourself whether sigma is known or not. Sigma known, sigma unknown. Okay. So far we have done all problems with the assumption where sigma is known, population standard deviation is given. Okay. So whether so if sigma is known, okay, then what is your standardized sampling distribution of single mean? I think there is a mistake here, typing mistake. Single mean, single mean. Okay. Simply sampling distribution of single mean x bar. Okay, then what will be the standardized variable for this, whether it is a small sample or large sample, whether it is a small sample or large sample, you take z equal to x bar minus mu x bar by sigma x bar. Okay, what is sigma x bar?
Sigma by root n.
Sigma by root n. Okay, sigma by root n, and sigma is known. Okay, this is under the case where sigma is known. Okay, so that is what you take to compute the probability. Okay, now when sigma is not known, when sigma is not known, you ask yourself whether the sample is large sample or small sample. Okay, so n what should I say, large sample or small sample, large sample or small sample. What do you mean by large sample? N greater than or equal to
Greater than or equal to
30, small sample n less than 30. Okay, so if you have a large sample, again don't worry, you simply define z bar equal to x bar minus mu x bar by, because sigma is not known, no, because population standard deviation is not known, you approximate population standard deviation with the sample standard deviation. Okay, sample will be given, okay, sample standard deviation may be given, or if sample standard deviation is also not given, sample observations will be given. By observing this, by taking the sample data, you compute the standard deviation. Okay, you take that in your calculations. Okay, what is s, where s equal to where S equal to sample standard deviation. Again, you can compute the normal probability because I have written Z. Whenever you see Z, that refers to that is an indication that you apply normal probability. So whenever sigma is unknown, but the sample is small sample. Okay, sigma is unknown, sample is small sample. Then then we should not use Z. Okay, we should take T. Okay, there is a variable called T. What are these Z? Z is nothing but a random variable, no? Like Z is a random variable, T is also a random variable. Defined like this: x bar minus mu by S by root n. Okay, so this is a random variable. Okay, so these two are random variables which will have normal distributions or approximately normal distribution. Their distribution is either normal or their distribution is almost looks like a normal distribution. Whenever the sample size is large sample or sigma is known and the population is normally distributed. Okay, but if sigma is unknown, if the sigma is unknown and if you are replacing sigma population standard deviation with sample standard deviation, then if you are defining a variable like this, it will have another distribution called T distribution. T will have a distribution called students T distribution. Students T distribution. Okay, T distribution are simply T distribution, or it is actually called as students T distribution. Okay, so this is about this. Okay, whether it is sigma known or unknown, we always assume that the population is normally distributed or approximately normally distributed. Okay, so we have problems on finding the probability only in the case when sigma is known. We don't have problems for sigma unknown case. Okay, and for sigma unknown case, these are called statistics actually. T statistic and Z statistic. These two will be useful in theory of estimation as well as testing of hypothesis. Okay, we are going to make use of these two statistics actually. Okay, we really don't have any problems on finding the probability that sample mean is in between so and so value and sigma is unknown. Is that okay? That is there only for sigma known case. Okay, so with this I want to conclude the second unit. Just look at the second unit topics. See, second unit is only 2 lines, but it took so much time for us to complete this unit. See, binomial distribution, Poisson distribution, these two are discrete probability distributions. Normal distribution, continuous probability distribution, sampling distribution of means, sigma known, sigma unknown. Okay, and we did problems on sigma known, and I have given a note what to do when sigma is unknown. Okay, so your portion for the first midday is going to be up to this theory of estimation. Inference theory onwards, it is going to be for the second mid exams. And theory of estimation is a small topic only, so I think we can complete your syllabus within the time frame. Okay, so point estimation, interval estimation, I said these are the two topics that are involved in the inference theory. One is estimation, other one is the testing of hypothesis. Okay, This is also part of inference theory only. Okay, I think this is third unit. Okay, this is third and fourth. Third and fourth both are part of inference theory only. Okay, third unit and fourth unit both are part of inference theory. Last unit is about correlation and regression. So units 3, 4, 5 divided to statistics. Units 3, 4, 5 devoted to statistics. Okay. So,
Sir,
if you have any doubts, you can ask me. I
sir,
stopped
it will
recording.
be